All right, this is the first example of chapter 9.2. It is question 195. Let's read the question first. Question 195. When a 180 nanometer light is used in an experiment with an unknown metal, the measured photocurrent dropped to zero at a potential of minus 0.8 volt. Determine the work function of the metal and its cutoff frequency for the photoelectric effect. So we are given two important pieces of information, notably the wavelength is equal to 180 nanometer. We are also given the stop voltage. This is the voltage at which the electric force is strong enough to prevent the photoelectron from crossing the space and reaching the cathode. In this question, at the beginning of the question at least, we are going to use the value of energy in electron volt instead of joule. You will see it will facilitate the computation. So just as a reminder, 1 electron volt is equal to 1.6 multiplied by 10 to the power minus 19 joule. All right. We will also need the charge of the electron, and this one is easy. It's simply minus E. So remember, the charge of the electron is negative. So the first part we need to figure out in order to solve that problem is the maximum kinetic energy of the electron, and this is related to the stop potential. We can find the maximum kinetic energy, which is equal to the charge multiply the stop potential. Basically, I'm gonna add the subscript S here. So basically, we multiply the charge, which is minus E, multiply by the stop potential, which is minus 0.8 volt. Combined, we get 0.8 electron volt. And this is the reason why it's more convenient to use the electron volt. Now, we learn in this chapter that light is a particle, but it is also a wave at the same time. And all the wave-like property still apply. Notably, the propagation speed, which is the speed of light, is equal to lambda multiplied by the frequency. So we can find the frequency, which is equal to 1.67 multiplied by 10 to the power 15 hertz. All right, we will need that value later on. Well, actually, we need it right away. Let's calculate the energy in one individual photon. So to find the energy in one photon, we multiply the frequency by the Planck constant, and we get 1.1 multiplied by 10 to the power minus 18 joule. It's, like I said, it's more convenient to have a value in electron volt, so we take that value and we divide it by the value for the electron volt, and we get 6.9 electron volt. So each photon that strikes the metal has an energy of 6.9 electron volt. Now, we now have enough information to find the work function. So the energy that binds the electron to the metal, the energy you have to fight against to let the electron escape to become a photoelectron. So we need to use that formula, so the maximum kinetic energy plus the work function has to be equal to the energy of each individual photon. And basically we got K max is equal to 0.8. We got the energy in each individual photon to be 6.9. If we combine everything, we get a work function that is equal to 6.1 electron volt. This is the minimum energy required for the electron to escape the metal. All right. Now the second part of the question asks us to find the cutoff frequency. The cutoff frequency is basically the frequency needed so that the electron get barely enough energy to escape the metal. And I will need more room to write the remaining part, so pause the video now if you need to write down this information, and I'm gonna erase the top part. All right. So the cutoff frequency happens when K max, or the maximum kinetic energy, is equal to 0. In other words, the photoelectron barely leave the metal, they have no energy remaining for the kinetic energy. So that means the work function has to be equal to H, Planck constant, multiplied by the cutoff frequency. Now we got the work function, it is 6.1. So the cutoff frequency is equal to the work function divided by the Planck constant, and we get 1.47 multiplied by 10 to the power 15 hertz. So at that frequency, the photon has barely enough energy to extract the electron from the metal. All right, so in the next video, we're going to be doing some more exercise to tie everything that we've seen together. See you in the next video.